So now I want you to stop for a minute. I want you to zoom out after all of this, intense derivation. Zoom out and let's see what we got. Yeah. So what we got is an error probability with diversity order n. And the array gain what? So we cannot even consider the array gain in its first definition because we don't have post-processing SNR. We don't have any idea actually how everything looks. But if we're taking a look at the array gain according to the second definition, then this was a shift with respect to the reference curve, and actually this is the array gain. According to the second definition. So we transmitted M spatial streams. Each one of them has diversity order n, and the array gain n over m. And I think this result is mind-blowing. I can tell you that the first time I derived this result was quite a long time ago, yeah, in my early days in MIMO. I looked at it, first I was amazed, and before I was amazed, I was confident that I have a mistake. I didn't believe this result at all. So I repeated the derivation again and again and again because I couldn't believe the result. Why? Why I couldn't believe the result? Why I consider this like a totally wrong result, even though it's right, yeah? Why? Why it's such an amazing result? Let's see why. So we have MTX antennas, and we transmit 1 over square root of m times S0, and so on. 1 over square root of m times S1, and so on. And we have n RX antennas. Okay. And the reason that I was so puzzled by this result is that I said, okay, let's say somebody made a mistake. Some engineer, and we're engineers, we make mistakes. So let's say somebody made a mistake, had a bug, and it transmitted only the first signal. And all the rest of the signals were simply not transmitted. I think you can agree with me that this situation for S0 is best because the other S1, S2, S3, they can only interfere. They cannot help S0 to be detected. But it still kept the normalizing factor, yeah? It didn't transmit the other interfering signals, but of course kept the normalizing factor. Okay. So in this case, what would be the optimal detector? MRC. Yeah? So optimal detector would be MRC, MRCN, yeah? Which of course has diversity order n. And the array gain, again, MRC, the classical, is also n, but because we introduced 1 over square root of m scaling here, array gain would be n over m. Amazing. This is exactly what we got here. So do you read my mind? Do you understand why it was so difficult for me to accept this result? The performance of each one of the spatial streams in spatial multiplexing, again, for complex normal 0-1 IID in the large SNR, is very well approximated by the performance of each one of them as if was transmitted alone. But he's not transmitted alone. Each one is transmitted with all the others, and they interfere, and so on. Spatial multiplexing, again, for complex normal 01 IID, is amazing because it actually, you can think about it like philosophically transform the decorrelation, we say, age guys. I'm just reminding you. They like translate or transform the decorrelation in the random variables into like totally orthogonal, mathematically orthogonal. If all the columns of age were orthogonal, we would have exactly that, or in case that the others are not transmitted. So the performance, to summarize, in spatial multiplexing for complex normal 01 IID, or the Rayleigh matrices, is like each one of these guys has been transmitted independently. So this is like a huge promise. So I want to take another step back and to remind you where we started, what we have. So we have a scheme. On the one hand, huge promise, yeah? In terms of performance. One hand is huge promise. But there's another hand. What is the other hand? We don't know how to implement the maximum likelihood decoder with reasonable complexity in most cases. So do you know what develops between these two nodes, in this gap? What develops? A lot of PhDs, yeah? So we have a scheme that has a huge promise, yeah, huge promise, but we don't know how to implement in a very reasonable way. So the area of coming up with, let's say, reasonable detectors that well approximate the performance of the maximum likelihood is still an active topic for research. A lot. I think I searched on Google yesterday. MIMO detection has over 6 million results in Google, because this is a very, very important point. I want to tell you two things. One of them is that in terms of terminology, in our business, in many cases, when people say MIMO, they actually mean spatial multiplexing. But from, let's say, from a correct terminology, MIMO, multiple input, multiple output, is like all the schemes that use multiple TX and RX antennas. But in our community, in many cases, when people say MIMO 4x4, they actually mean spatial multiplexing. And the second is that I've spent a lot of my years in trying to come up with a good approximation for the maximum likelihood with reasonable detection, complexity of detection. So in the next lecture, I'm going to give you just a glimpse of maybe the most important MIMO detector families, so that these results can also translate into something very practical and very important.